Okay. Yeah, we have the last speaker now, Masayuki Kimura. He is an engineer at Tenstorrent in Japan. He is currently working on designing chiplets with RISC-V CPUs. He has more than 10 years of experience as a microprocessor design engineer. Recently, he went back to academia, the University of Tokyo, to pursue his PhD degree on CPU microarchitecture. Please welcome Mr. Kimura.
Yes, thank you for your introduction. And this industry session starts from wireless communication, and next wired communication, and finally it's computer architecture and instruction set architecture. I think it is a great transition. And so my topic is about computer architecture. So please relax. My slide doesn't include any of difficult circuit or difficult mathematics. So please relax. Okay, at first I little bit introduce myself. My name is Masayuki Kimura. I am a design engineer from Tenstorrent. This is Tenstorrent is a semiconductor company based on Canada and US, and we also have a Japanese branch, and I work for the design engineer designing the SoC with RISC-V, and from 2022, I am a PhD student at the Graduate School of University of Tokyo, and my research topic is computer architecture and vector processor. This is an outline of today's talk. At first, I a little bit explain about what is RISC-V, and I will explain some of the examples that RISC-V has entered the population phase, and next I discuss some of recent trends in RISC-V specification, and finally I little bit introduce Tenstorrent approach with RISC-V. Okay, so at first, actually, I'm little bit afraid about almost of you are the analog design guy. So could you raise your hands if you know anything about RISC-V? Oh, about 10%? Yeah, so yeah, I think I need to explain about the basic topic. So, okay, RISC-V is the instruction set architecture that is open source instruction set architecture that is developed by the University of California, Berkeley. So you can imagine RISC-V is some kind of like x86 or ARM. And recently, RISC-V recognized as the third major ISA following with the x86 and ARM. And the strong point of RISC-V is its openness. So it means that if you implement a CPU based on RISC-V, you don't need to pay money, and we can use freely to implement CPU based on the RISC-V. And it also that it doesn't mean the open source that all of hardware implementation need to be open. So many of CPU vendor start to develop RISC-V CPU and they sell it. Okay, RISC-V specification is managed by the RISC-V International, that is a non-profit organization, and it prevents any single company from by monopolizing the ISA development. For example, some of ISA like x86 or ARM has some problem like x86. Only Intel can decide the change of this specification, and very few company can implement the hardware that support x86. And ARM case, generally it needs a very expensive architectural license cost. So maybe you know that ARM and Qualcomm has dispute over the architectural license cost, like the Qualcomm Snapdragon CPU IP. So to avoid such kind of problem, the goal of RISC-V is to be simpler than x86 and avoid the issue of royalty. Okay, the basics of RISC-V. The RISC-V instruction set is designed to be very simple. It means the mandatory instructions are designed to be very simple. So it means that a minimal set of basic, it consists of minimal set of basic instruction like base instruction, and the function is extended by the extended specification like multiply and multiply instruction or supervisor instruction or vector instruction is defined as an extension. So the strong point of RISC-V is its modularity, that is the base instruction and the extension is completely separated. So any CPU developer can choose the extension optimized in their application, so they can customize the CPU for their application use case. And the mandatory set of the RISC-V, the basic instruction set, consists of only 4 types of encodings, like register-to-register operation, and register-to-immediate operation, and store, and operation is long immediate operation. It keeps very simple. So CPU developer can easily to start the RISC-V, easily to start the develop of RISC-V CPU. And RISC-V has recognized as the third architecture following the x86 and ARM from this open from 2011. And the software side of view, RISC-V becomes well established. It's, for example, Debian, last year, Debian project announced that support for RISC-V as an official architecture. And especially in China, development has accelerated rapidly. This is due to the US and China semiconductor competition, and almost all of the microcontroller developed in China is already replaced into RISC-V. And the field of academia, RISC-V has become a standard, and many university class or course already now are based on the RISC-V. And many research papers on computer architecture are already based on RISC-V. And there are some examples that big IT company transition to the RISC-V. One example is that NVIDIA this year has announced that the gradual replacement of Falcon microcontroller within their GPGPU into RISC-V. It means that around 1 billion RISC-V core are expected to be shipped in this year. And last year, Google and T-Head, that is Alibaba's semiconductor division, collaborating to enhance the Android support for RISC-V. So I believe that this collaboration is a big enhancement of software development of RISC-V, especially for the mobile applications. So if you want to first step to getting started with RISC-V, there are many ways to start. The software side of view, RISC-V has become nearly barrier-free. Some of the tools, including operating system, compiler, and simulator like GCC, LLVM, Linux, QM, already support the RISC-V architecture. And many of the development boards are publicly available, so that includes Linux can be some of big development boards that can boot Linux, or other very small size of development boards for use for IoT. And the field of academia, in many architecture research projects, RISC-V is chosen as their evaluations. And many of the general simulator like GEM5 and QM already support RISC-V. And other research dedicated cycle accurate simulator like Olympia or Sniper is also support RISC-V. In my case, is also I research about microarchitecture, so I use RISC-V and such kind of Sniper, such kind of simulator, like for example Sniper, we used to evaluate my method, my proposed idea is has an effect or not. So sometimes we can generate such kind of pipeline viewer to confirm my method has a really effect or not. Okay, let's move to recent trend in RISC-V specifications. As I said, RISC-V, a strong point of RISC-V is its modularity. So I show this graph, this figure that base instruction and extension is completely separated. But actually, this graph, this figure, I draw about over 10 years ago. I draw this figure, and recently, the situation becomes changed. There are many extensions are defined by the RISC-V International, and thousands of instructions are ratified. So I think that this is sometimes some of the chaos situations, and the biggest problem of this many of the extensions defined is how to manage the compatibility of software that supports CPU. So to solve this such kind of situation, RISC-V International is recently introducing a new concept that is a profile. The purpose of a profile is to ensure the software compatibility across the extension. So each profile standardizes the mandatory instruction set. For example, if there is one example that RVA23, that is the name of a profile. That is if some CPU developer choose the support of RVA23 profile, it needs to include the mandatory extension like multiply and add, multiply and divide extension, atomic extension, and finally vector extension need to be included. So software developer can be recognized which profile is supported in the dedicated CPU. So I'll explain later how to software guarantee or how to software compile to support such kind of profile. And other purpose of profile is maintaining the compatibility of legacy software. So each profile is updating the year by year or 2 years at once. So the older version of profile is fixed, and if the software is compared with older version of the profile, it can say that the software already fixed, and they can keep the compatibility with older software and hardware. So this is the image of profiles. So there are many extensions defined. And for any profile, for example, application processor, high performance application profile, it chooses some of the mandatory extension, and some CPU must support all of their extension. And other kind of profile that, for example, microcontroller, other kind of extension should be included. So CPU developer can choose choose a profile and choose an extension for their application use case. So for the software side of view, if you want to compile some software using the LLVM clone, just this option, like to specify RVA20 to use the RVA23, so the compiled binary is guaranteed to run correctly that supports CPU. supports the CPU that support the RVN23. And on the other hand, so for example, if you use other kind of CPU that are a little bit older one that support RVA22, it have it can easily recognize that there is a software doesn't have a software compatibility, and anyway, RVA23 binary can be run on RVA22 CPU, I believe, but there are many overhead or some additional execution is needed, and it becomes high performance problem. So, in summary, this profile concept can easier to interact between compatibility of software and hardware, and programmers can build software by assuming the presence of a certain extension based on this profile concept. Okay, finally, I little bit talk about Tenstorrent approach with RISC-V. The Tenstorrent is actually the AI accelerator company, but we also implement RISC-V CPU called Ascalon. The Ascalon is used for the high-performance CPU, and it supports RVA23 profile. And it is developed for the host processor for AI accelerator. To use this RISC-V CPU, we have a Japanese project. In Japanese team has a project that making a CPU chiplet with RISC-V CPU. This is actually joint project of LSTC, that is IST and University of Tokyo and Rapidus. And Tenstorrent's task is to implement the CPU chiplet using a RISC-V with Rapidus 2nm technology. So I believe that RISC-V, we can use RISC-V, and we can implement the CPU chiplet optimized to control the AI accelerator. And finally, our target is making to such these chiplets that include AI accelerator and CPU chiplet and memory chiplet. This is we are still ongoing on the Japanese Tenstorrent Japanese team. Okay, this is a summary of my talk. I introduced RISC-V and some of recent trend of RISC-V specification. And finally, I little bit introduce our project in using with RISC-V. Yeah, thank you very much.